Thanks, Sam. I'm recording now.
Great. So good morning, everyone, and welcome to today's event from Montreal NLP Consortium, which is going to be the last from this season. So similar to all the other events, we'll have three very exciting talks today. I'll briefly introduce the speakers for today's event. So our first talk is going to be by Eloi Brassard-Gourdeau, who is a data scientist at Two Hat Security and is going to present using sentiment information for preemptive detection of harmful comments in online conversation. The second talk will be by Hannah Devinney, who is a PhD student at Umeå University, and they're going to present gender bias in NLP, a short introduction. And the last talk will be by Carolyne Pelletier, who is the co-founder and CTO at skritswap, and the presentation title is Gender Bias in Natural Language Processing. So before we move on to the speakers, I would like to ask everyone to, if possible, turn off your cameras and mute yourself during the presentation by the speakers so that everyone can enjoy the talks by the speakers. And lastly, every presentation will be followed by a 10 minutes, about 5 to 10 minute period for the question and answering. So if you have any questions, it would be great if you can write them down and ask them at the end of the presentation by the speakers. So without further ado, we're moving on with the first talk by Eloi Brassard-Gourdeau, who's going to present using sentiment information for preemptive detection of harmful comments in online conversation. So Eloi, the floor is yours.
Okay, thank you. It says video sharing is disabled by the administrator. Is that on your side? Is that because of my account?
Guillaume will give you the access right away.
Okay. Yeah, I can share content. I just wondered for the camera since it's good to see my face speak. But
yeah, sure. Yeah, we'll definitely need your slides to present.
You should be able to present Eloi. It doesn't work.
Hang on.
Yeah, now.
Yeah, I'll just move it around. It's just my camera I won't open, but it says, yeah, the video sharing is not working, but I guess you won't see my face when I'm talking to you, but no big deal. Okay, so you all see my slides right now?
Yes.
Yes, you can see.
Okay, cool. So hi, as already presented, my name is Eloi Brassard-Gourdeau. I'm from Two Hat Security. Formerly a student at University Laval in Quebec City. And today I'm going to present using sentiment information for preemptive moderation of online conversations, which is something I co-wrote with my supervisor, Dr. Richard Coury, during my master's degree, and we recently presented at Canadian AI, which was last May in, well, virtually, but technically in Vancouver. So without further ado, I'm going to start on explaining a bit why we did this work. So as probably most of you know now, internet is now a huge means of communication. Billions of messages are sent every day, and a lot of cyberbullying is happening, and a lot of harmful content is shared, and a lot of what we call, well, what is called sometimes toxic content happens. And most of the recent works in research have been done on single line detection, which also include work we did before, which I'm going to talk about in a second. But yes, so most of the times it's basically post moderation. So tools exist right now, and at Two Hat Security we also work on a specific tool that does that, which basically helps filter out content or dangerous content after it's being written. But what we wanted to work on was a way to help preemptively detect if a conversation is gonna go awry, or it's gonna turn harmful, so that we can, or well, either automatically or moderators can more easily monitor where to look at and what might turn dangerous or harmful for users. And for that case, obviously using entire conversations is necessary. And this is something that has barely been done so far. Like there's a few researchers and a few more that happened since we wrote this, but yeah, it's still a very new field of research. So we mostly based our work off on a paper called "Conversations Gone Awry" by Zhang et al., which looks at two conversations together, one of them going awry and one of them staying healthy in a way, and then trying to predict which one of them is gonna go into like the insult train and that kind of stuff. And in that specific research, they used sentiment information, but they felt like it was not useful in their case. But our intuition and work we did previously suggests that it should be useful, and intuitively it's pretty simple. I mean, if people are talking about something, like in my example I've got down here, people are talking about something like hate speech in a calm and rational conversation, they might just be talking about the issue, talking about problems relating to hate speech, but not using hate speech related insults. But then if the conversation is heated, if you've got lots of negative sentiment in there, then there's a good chance that there's actually some hate speech happening right now in this conversation are about to happen, and you're going to see hate speech related attacks. So intuitively it should work. And their work it didn't, but basically what we want to do is show that if we do it better, then it can be very useful. So to do that, we used previous work we did, as I mentioned, in an article called Subversive Toxicity Detection Using Sentiment Information, in which we created a sentiment detection tool, which allowed us to be better and as I said, in single line toxicity detection. So in specifically subversive context. So what I mean by subversive is if someone tries to hide their words, so like change the characters, use leet speak, use any kind of ways to mask their harmful messages, but we should still pick up the negative sentiment from it. And then we had some decently good results where sentiment helped. So we're basically going to reuse that same sentiment detection tool in a new context. And this tool is based on lexicons. We used in the other work, we used about 6 or 7 of them, but in the end, we found out that only 3 of them were mostly useful, which are SenseWordNet, AFIN, and Bing Liu, which I won't dive really into, but it's basically assigning positivity or negativity scores to words. And we also take into account negation. If someone says this is bad, or if someone says not bad, then that doesn't mean the same thing. So we take into account negation. We take into account some idioms, like, I don't know, give up or that kind of stuff, which give or up are both generally positive words, but give up together kind of seems more negative. So that's generally how the sentiment detection tool works. I'll go over quickly on that since it's not the focus of this work, but if you have questions at the end, I'll gladly answer anything related to that. So our first experiment, what we did was basically, as I said, we based ourselves off of the work called Conversations Gone Awry, which uses a data set from Wikipedia edits. So for anyone not familiar with what the edit wars in Wikipedia are, is sometimes there's conversations happening on Wikipedia articles where someone edits something, then someone like disagrees and they edit, and there starts an edit war, and people often start to insult each other and call each other names and that kind of stuff. And it's a common data set used in toxicity detection. But what they did here is they took a bunch of conversations, and those conversations had to follow some pretty general guides of having at least 2 conversations on the same topic. So not completely different topics. So sometimes 2 conversations on the same article or on similar articles. And those 2 conversations needed to start in a civil way. So the first 2 messages should be like no insults or no major harmful content. And then one of the 2 needs to stay civil the whole time, and the other one needs to basically go into insults or name calling or that kind of stuff. And then what the model wants to do is between those two conversations, just looking at the first two messages. So technically, there's no harmful content at that point. Just looking at those two first messages, predict which one will stay healthy and which one will become toxic. So we reuse the exact same data set, and we reused most of their features. So from their work, they were saying politeness strategies and conversational prompts were the most predictive features. What they mean by politeness strategies can be used of the first person, use of second person, say please, thank you, hello, or be super direct, use the subjunctive, use hedges, like would and should and that kind of stuff. So these are the politeness strategies and conversational prompts. They use, it's basically they did clustering of, so unsupervised clustering of how the conversation started, so of different prompts, and then tried to classify them into different families. So we didn't change any of that from their work. We just took that and then we plugged in our sentiment detection tool in there. So what we did was, what they had in their work was basically, is there a positive word? Is there a negative word from one specific lexicon? If so, the feature was 1. If not, the feature was 0. And there was basically just 2 features. What we added here was for each message, we had basically 6 features. So 3 of the most positive words and 3 of the most negative words. And then for both messages, we calculated the tone of the message. So basically positive minus negative. If the score is negative, then it means the tone of the message is negative. If the score is positive, it means the tone of the message is positive. And then basically did a one-hot encoding of that. So you have either 2 positive messages, positive then negative, negative then positive, or 2 positive. So this gives us 4 extra features. So this gives us a total of 16 different features. So we replaced basically those 2 sentiment features by our 16 sentiment features to basically prove that we can use sentiment in this situation. So before plugging it into the model, we just basically did a general test of what the original sentiment has as a predicted value, which is 51, which is basically random chance, because you're always 50-50 of choosing the correct message. Our sentiment has 55.7. Then the tone doesn't really convey anything with 50.8 and all the features together. So adding all those up together, we're at 55.8. So what we did basically from there is we just kept the sentiment. So we just kept what I said here, the 3 most positive words and 3 most negative words for one message. And that's it, because the rest isn't better than basically random or chance, or barely better. So it's not useful to add all those features in. And then we took their text features and reproduced their result, which is 58.6, which isn't great, but it's early work, so it's still not too bad. And then we added sentiment in here, so added those 12 features that you see here. We added them there to have a total of 50 features, and then we got the results up by 2%. And this is using some basic logistic regression model with feature selection. So a gain of 2% can seem pretty small, but since we're at 58 before, it's kind of a decent step forward, because it's a very difficult task. It's not like general single line post hoc detection. It generally gets better results than this, but here we're basically just trying to flag anything that might be dangerous. So we're catching, I guess, 10% of conversations more than random chance, which is pretty good at this point. And then what we did was we basically wanted to go a bit deeper and push our result further, because we're really happy with 60%. So we try to look at what are the most important features, most important negative and most important positive features. In the case here for negative features, you see negative sentiment 1, negative sentiment 2, and 3 come up. When there's a second in between parentheses, it basically refers to the second message. Because as I stated before, we're looking at the first 2 messages. So we basically have the 3 negative sentiment from the first message and the 3 negative sentiment from the second message. And the most important features were the second person, which matches the results from conversation gone awry. But then negative sentiment comes in at second, and the 2 others here come in pretty close. However, for positive sentiment, only positive sentiment 3 and the second messages comes up. So what that made us think about is that strong negative words, as you see here, so negative sentiment 1 and 2 come in pretty high, so they seem to have more impact, but positive words, you need more positive words. So since it doesn't matter if the first or second positive words is very strong, you need a lot of them, so you need at least 3 of them, because generally messages are very short, so 3 positive words is a high number. So you need a lot of them to have an impact. So what we did to basically change it around is we then experimented by changing. So we had 3 positive and 3 negative. And then we basically did a grid search, trying everything between 1 and 7 for both positive and negative. And then our best results, we managed to get 1 extra percent. So we got up to 61.6 here. So 1.1 extra from that 60.5 we had before by using 2 negative and 5 positive. 2 negative features and 5 positive ones, which matches what we observed first here in those points here. And when we look at those new feature importance, then you see negative sentiment 1 and 2 still happening. We just replaced the third one by the 2-second message. But then positive sentiment 4 and 5 come up a lot higher and with a pretty high importance. So this fits with the general observations we had of having a bit of positive words or a couple very strong positive words doesn't really impact anything, but having a lot of positive sentiment has a higher impact, while having just a little bit of strong negative sentiment seems to be enough to completely change a conversation, basically. So I've got a couple examples here that are well, they're selected cases where basically, without the sentiment features, the model got wrong, and with the sentiment features, the model got right. So here, there's only like 2 positive words that are like kind of have a strong weight, which is pretty. But then there's the failed, there's the useless, there's the worst, there's the problem, which marks a slightly more aggressive, I'd say, way to talk about stuff. And then while not using sentiment features, we got this wrong, but when using sentiment features, we got this right, and this correctly derails basically because of the bad words and the general aggressivity of the tone. And there's a second example here, which is doesn't really fit with what the data sets are, because there's a direct insult here. Sorry for the strong language, but it's what happens in the data, and it's really not the worst that we've seen. But yeah, it doesn't really fit their description of no strong insults in the first 2 messages, but I mean, it's still another example here. I think there's someone's mic that's open. Okay, and now I'll be moving on to a second experiment we did. So our first experiment was kind of conclusive, but we wanted to try a completely different context, just to see if something works in one context but doesn't in another, then it doesn't really help. But we wanted to try it out. So since Two-Hat Security, the company I work with now, but we worked in parallel. During our study, works with a lot of gaming chat company, gaming companies that have a lot of in-game chat. We had about 30K conversations of up to 50 very short messages. So it's a completely different context in the sense that in the edit wars, like sometimes you have those kind of comments that are pretty long, but in gaming, live chat from gaming, general messages are 4 words. I think we had a 4-word average of a message. So we can't really only use 2 messages, because sometimes we're only going to have like 6 words or like 5 words to work with, which is not really enough to know what's going on. So instead of using 2 messages, we use the context of 10 message. And then what we have basically is we have 1 message that's been reported, and then a moderator says if it's actually offensive or harmful or not. And then we use the 10 messages prior to that message. So to know if the 10 messages before correctly leads us to that offensive or harmful message. The data set is much harder here because there's a lot more users interacting. It's not only a couple of people. Sometimes in those 50 messages, you have 40 different users or something. Sometimes there's more than one conversation going on. It's like basically it's a mess. But might as well give it a go and try. And we have 30K conversations, so that allows us to do some more advanced AI that the smaller data set from the other experiment did not allow us to do. So here what we did is we basically used to model. We used the same linear regression that we used on the first data set, and then we used a RNN, more specifically a GRU unit that we basically developed in our previous work, and we used it in a conversational context. So basically it looks at one sentence after the other and updates its scores. And here are the results. So the ones with 260 features, here you see there's a lot more features because there's 50. We're using 10 messages. So we're adding a bunch of features for all those messages, and we're adding 70 of them because there's, as we remember, we have 5 positive sentiment features and 2 negative sentiment features. So that makes 7 per message times 10, because we have 10 messages, we add 70 features. And the 190 are the politeness strategies that we have here. We kind of scrapped the whole conversational prompts side because it was too much, it took too much time and didn't really mean anything to work on conversational prompts in a live chat context. So we used here, there are 19 sentiment features plus 7, so there are 19, sorry, politeness strategies features plus our 7 sentiment features, and then multiply that by 10, it gives us 260 features. As you see here, the regression doesn't really learn anything. In this case, with only the politeness strategies, but adding sentiment, it goes up by 7%, which is huge. In the RNN, we managed to learn something on the politeness strategies. Sorry, that was unintentional. And then we once again got an about 1% raise off of adding the sentiment features. But then we once again try to push our analysis a bit further. So this second table here is a bit more complex. I'll come back to it in a second. Let's just look once again at the feature importance. As you see here, negative sentiment 1 and 2 scores very highly. It's like the top 2 features, and in the first message before the one that's reported. So this number here is basically the one just before, or like 10 messages before. And then here we have subjunctive scoring first. Small asterisk, though, there's about only 1.6% of the messages of our data set that contains subjunctive. So it scores very highly, but it's not that relevant a feature because it nearly never happens. Positive feature 5. There's a number missing here, I'm sorry. I'll need to recheck, but one of the positive features then scored the second highest. So what we wanted to do then, since we've got 10 messages, we wanted to see if it's more relevant. It's really relevant to look at those 10 messages, or only the few messages before are important to look at. So if we go back to that table here, basically this is a chronological order. So if the message 0 is the one that's either harmful or not harmful, then those ones are going back. So if you look at the negative features, most of them are concentrated in the last 3 messages. We have basically 12 out of 24. Or 12 out of the 24 that are here. Well, positive is spread out over the whole conversation. So then this basically indicates that only the most recent messages matter. And we then replicated the experiment by not using 10 messages, but using only the 3 last. So basically, instead of using 260 features, we used 26 times 3, so 78 features, and we replicated the exact same result. We had 71.8, so it's in between the confidence interval of being the exact same thing. So basically what this tells us is that we don't need to look at a lot of context because the conversations change really, really quickly. And that kind of fits with the result we had in the first. So To conclude this, we had 5 major conclusions. But the first one, most obvious one, is sentiment is indeed a predictor for harmful messages, and that it should not be discarded, even though other researchers have kind of discarded it, and we kind of think we proved that it's useful. Second is that sentiment information is found at the word level. So as the previous work said, sentiment information is not useful. They didn't really look at the word level, they looked at the message level. And then when we tried doing the message level ourselves, it also did not work, which is the results of the tone that we had earlier. So that if we want to use sentiment information, we can't just say this is an overall positive or this is an overall negative messages, because it doesn't really indicate what's going on. We need to look at the word level. And then thirdly, it takes a lot of positive words to have a healthy conversations, and basically they're spread out over the whole they need to be spread out over the whole conversation. But then only if like a couple of really strong negative words happen, then that's the indication of something about to turn or already turned toxic. Then that's enough, and you don't need to balance the whole positivity thing. It's just gonna basically go awry pretty quickly. We can also say that the predictive features were consistent over 2 very different formats of conversation. So the results were similar. The same kind of features were the most important. So while we can't say it works for every context, we tried 2 very, very different contexts, and they both worked. And then finally, it kind of goes into the third point again, but a conversation can turn harmful very quickly. So we don't need to look, and that fits with other works that there's here, that a work I managed to talk with the authors of Carolyne, which is Preemptive toxic language section in the Wikipedia Commons. Basically, they have the same conclusions of if you look too far back, then it doesn't help anything, and it's not it doesn't give you basically any useful information. So when looking at doing some preemptive or predictive moderation, you need to look only at the most recent stuff, because it doesn't really matter what was said before. And yeah, here are the main references, and yeah, that's it for me, unless there are any questions.
Thank you very much for your great presentation. So we have about 10 minutes for the question from the audience, and we already have the first question by Malik. Please go ahead.
Hello, can you hear me?
Yes.
Okay. First of all, thank you very, very interesting talk. My question is, like, based on my understanding, you have two components are here. You have the style of saying things and the content, the message. And in some cases, these two work together, so reinforcing each other, which is good. But the problem is when, like, you have a polite style of saying something very rude. So do you think maybe changing this to a multi-class classification, where you're instead of saying this is a hate speech directly, you would predict the style and then the sentiment, or like the content, and then look at specific examples exactly to see what's going on, or like decide based on the outcome of these two classes, maybe weight the content more than the style?
Yeah, that's actually a pretty good idea. In a way, the politeness strategies kind of confer to the style. That's kind of what we wanted. In a way, what we wanted to do by adding the politeness strategies is one is not the sentiment information is the politeness strategy is more about the style and how it's said, and then the sentiment information is more about if it's said negatively. So something can be said with general politeness strategies, with like saying hi, but then being super direct and super negative over what some, like, let's say, I think you're really wrong, or what you're saying is blah blah blah, and that kind of stuff. So it goes a bit in a way what you're saying, but I kind of like the approach that we didn't do of doing some multi-class, or trying to split them both up and then match them together to get more meaning. So we didn't do that, but that's actually a good idea for future work. Yes.
Thank you. Thank you.
We have more questions. Fabrizio.
Yes, thank you, Eloi, for your presentation. I'm not entirely sure I understand the number of messages. When you look at the messages to detect toxicity, do you only look at the messages of a given user or the replies that this user gets? Because I guess that's an important signal whenever you try to detect toxicity. When someone in a Wikipedia discussion for an article says X and someone else replies, your insults are useless here, I guess that's an interesting signal as well. So which is it? Is it only a single person speaking, or do you also look at the replies?
So we look at everyone. However, it's preemptive in this case. So we're looking at what was said before any harmful content was said. So we can't analyze the replies because we're only looking at. So if someone, I don't know, if someone says a big insult, then we look at what was said before and not what was said after. But we don't look at what was said exactly too. We basically try to predict if predict that this insult was going to happen based on what's happening before. As for what the labels were, so how the negative content was classified by the moderators, that I don't really think they look at the replies, no, because it's really based on what was before and what was said, but not what was said after.
Okay, so you look at the messages that are said by a single user, and not their replies. You ignore them when you try to classify preemptively.
Well, I mean, technically, since we're doing it preemptively, the replies haven't happened yet in the practical context. Like in theory, if you try and do it preemptively, you don't have any replies because your goal is to make that first message, that first negative message, not happen in the first place. So before the first message happened, we don't look at a single user. We look at all the users that are talking. But then we don't look at what happens after that message. It's really a time difference in preemptive versus like post hoc intervention, which we could look at the replies. But since technically no replies would have happened yet, since we're acting earlier on, then we can't look at the replies.
Okay. Thank you.
But yes, in single contexts, I would agree that if you're doing some post hoc detection and you're trying to, like a conversation happened and then you want to delete the harmful stuff, then you can probably look at the replies, but it doesn't really apply well in our case.
I see. Okay, thank you.
Thank you.
Thank you. So we have a question by Guillaume.
Yes, thank you, Eloi, for your presentation. I was just curious about your strategy to identify which words are positive and which one are negatives. And especially, are there like context aware? So in the examples that you showed us, for instance, if someone states that I'm pretty disappointed, for instance, will the word pretty be associated as a positive or as a negative word?
Yeah, so it's a lexicon-based approach, so it has flaws exactly like the one you stated. So there are some lexicons online. As I think, hang on. We use 3 of them, which can still be found and are referred to in our paper, which are these 3. So they're basically just a huge list of like tens of thousands of words, which with positive and negative weights to them. One of them said a word made by unsupervised learning. The other 2 just by human doing, like basically putting words and assigning scores. But yeah, in this case, the pretty would be a positive word, even though it's used to amplify a negative word. If someone says it's pretty useless, then yeah, it's gonna amplify the negative word. So I guess that's kind of why we see that positive words, a few positive words aren't really an indicator. It's because that's a flaw in the lexicon-based system, is that you can't really take those into account because, yeah, sometimes they're going to be wrong. So yeah, it's not a perfect approach, but since there's lots of people working on AI-based or a lot more solid, I guess, sentiment detection tools right now, the goal was to basically only use one part of AI and say, like, if we're using sentiment, like basic sentiment information, we can get stuff done. So with more advanced sentiment detection, we could probably get even better results.
Thank you.
We have time for one last question. Yeah, Fabrizio again. Let's go ahead.
Yes, I have a second question about the RNNs that you mentioned in your presentation. If I remember correctly, there are something like 300 features that you use in your RNN. Does that include a word embedding, or are these 260 features that do not use word embeddings? Because I guess the embeddings are very useful.
Yeah. I skipped through that whole part a bit too quickly. So yes, we are using embeddings. No, those 260 features do not include the embeddings. So what the model does is, I should have included a graph of the architecture, but we basically have a GRU unit working on the embeddings of the words, and then we're merging through linear and ReLU layers. We're merging the 260 features to the output of that GRU unit that's on embeddings. And then we're taking all those, basically the embeddings plus the 260 features, we're feeding them through another layer of recurrent network that goes one message after the other. Does that make sense?
Yes, thank you.
Yeah, should have included a graph, but yeah, forgot about that. Sorry. Good question.
Thank you very much again, Eloi, and thanks everyone for the questions. We are moving on to the next speaker, who is Hanna Devinney, who's a PhD student from Umeå University in Sweden, but is joining us from the US. And they're going to present gender bias in NLP, a short introduction. So without further ado, Hanna, the floor is yours.
Thank you. I just need to figure, oh, okay, great. So you can see that presentation, right?
Yes, great, thank you.
Cool. Okay, let me just pull up my notes also, so I can see my presentation. Okay, good morning. My name's Hannah. My pronouns are they, them, and she, her in English. Elle is fine in French. I'm a PhD student at Umeå University in Sweden. I'm doubly associated with the Department of Computing Science as well as the Graduate School for Gender Studies. And very broadly, my research focuses on gender and NLP. Specifically, I look at bias in language data sets. So currently, this is trying to come up with computational methods in order to identify gendered patterns, and then using feminist and queer theory in order to develop methods for looking at those computational results and understanding the patterns and themes in a way that can help us curate our data sets to be more fair. So today I'm going to focus a little bit more on the theory side, because I think as a gender studies person, like that's a helpful thing that I can bring to the table here. And hopefully this will help set you up for thinking critically about gender and bias in natural language processing and segue nicely into Carolyne's presentation. So first things first, defining gender bias is really quite difficult. So we're going to start with an example that I found is sort of the prototypical way that people who've been exposed to the concept of gender bias in NLP in general, but who haven't like taken a deep dive into reading all of the available literature about it, think about bias. So we have a translation task where we're going from a neutral or ungendered pronoun so in a language like Finnish or Turkish, to a gendered pronoun in a language like English or French in a way that reinforces stereotypes and gender roles, and that makes this translation biased, according to some definition we're going to come up with. So for example, let's say we have a sentence that says, I talked to the nurse and blank said, where the pronoun in the source language doesn't indicate gender. So do we want to translate this with he or she? As an arbitrary but not like actually unrealistic number, I've suggested that our fictional system is deciding only between these two pronouns, and it thinks that she is 95% likely to be in this gap, and he is only 5% likely. So obviously, like looking at this line, the green is very long, and that seems pretty biased. But what would it actually mean for the system to be unbiased? What would that look like? On the one hand, it's translation, so the goal is to be correct. Lacking any other context or information about this nurse, maybe we should just guess based on population statistics. So in the US, 85% of the time she would probably be correct, and in Canada, about 91% of the time she would probably be correct. Obviously, we don't have this context or other information though, so maybe it's a better idea to be fair and to attempt to avoid the stereotype half of the time. So should we flip a coin? These are two really different amounts of bias. Like those arrows are quite far apart on this scale, and both are definitions that are used in different pieces of the research in the field. Also, we're kind of diving right into defining bias or what's fair, but we've skipped a step. We have to define gender in order to figure out why this stereotype of nurses being she's is an association that we have or a problem in the first place. So the example makes a really big assumption about gender, which is that it's binary. We're only looking at two different pronouns, he and she. We can add in some other assumptions that we might have been using to try and be more correct if we start looking at more information. So for example, we might be thinking, oh, if we could track this nurse throughout the rest of the document that we're translating, we could perhaps figure out what the right pronoun is because maybe it's used earlier or they're described one way or the other, but that assumes that gender doesn't change for a particular person. And we also might try to include some multimodal information, maybe a picture of the nurse, then perhaps we could pick the right pronoun. But that's assuming that we can identify gender from physical appearance. And so these three assumptions are the core parts of what's called the folk model of gender. This is the dominant understanding of gender in Western or European influenced society. And it's a narrative that Judith Butler described in the 90s in terms of the heterosexual matrix. Okay, we don't have a whole lot of time to define the heterosexual matrix, and it's kind of in-depth theory. So I'm going to summarize pretty quickly, but feel free to make me circle back to it if it doesn't make sense. The heterosexual matrix describes the way that artificial taxonomies of sex, gender, and sexuality are made to seem to be the natural way of things, and the way that a person is only accepted as coherent to society if they fit into this schema. So the schema goes, you have a body, which according to a doctor inspecting your genitals at birth is assigned either male or female. And this assigned sex determines, so that's what this arrow is doing, this diagram, your gender and gendered behavior. So if you have a male body, then you're a man and must dress and behave in a masculine manner. And if you have a female body, then you're a woman and have to dress and behave in a feminine manner. Part of behavior is desire, and the schema tells us that only straight or heterosexual desire is acceptable. And it also kind of loops back around into gender because being heterosexual or exhibiting heterosexual behavior is part of what makes one a real man or woman. So the problem with this, obviously, is that there are a lot of people for who these lived realities don't fit into the assumptions. And when systems are designed based on those assumptions, then you leave us out. So if you don't fit into the assumptions, the society doesn't see you as normal. And in fact, you're something abnormal or other, a them and not an us. And that makes you much more likely to be a target. A lot of the examples I'm about to give on this slide are sort of really bad consequences for trans and gender nonconforming people like myself, but bad news for all the cis people in this audience. The consequences aren't good for you either. Cis women in particular suffer a lot under this model because it sort of encourages us as a society to reduce them to sort of an objectified version of gender that's really heavily based on their bodies and their roles as carers. Whereas cis men suffer a lot of pressures to conform to an ideal of masculinity that's not sustainable, and that tends to lead to really severe mental health consequences and very limited means of reaching out for support when these mental health crises are happening. Anyway, being unintelligible to humans can put you at risk of violence, and being unintentional to computer systems also puts you at risk of violence, although the violence is often coming from humans. So for example, airport security scanners typically only have two modes. There's a button that the person running the scanner is pressing to decide if they look at you and say, oh, you're typically male, you get that button, you're typically female, you get that button. And if your body doesn't match the button they hit, then you're going to be subjected to more invasive and dehumanizing searches. And obviously that's a pattern that affects some people more than others, people who do not fit the assumed model of cisgender. Being correctly gendered can also be a problem. For example, if your social media data is connected between a personal and a work persona, then you might be outed in an unsafe environment. And there's constant misgendering from computer systems. So there's the machine translation like we saw above. There's getting targeted advertisements that don't apply to you. There's automatically generated emails assuming your title and it's incorrect. And of course, facial recognition just sort of being itself and deciding. And the facial recognition in particular is compounded by intersecting factors. So we know that facial recognition performs much worse for dark-skinned Black women than it does for light-skinned women, and it performs best for light-skinned and white men. Okay, the other major point jumping off of intersectionality that I need to make about gender is that gender is not the only thing that contributes to gender, and it's definitely not the only factor that we have to worry about when we're addressing bias. So intersectionality is a framework for understanding how social categories interact. In research, I like this quote from Anne Phoenix a lot. It's the understanding that everybody is simultaneously positioned within social categories such as gender, social class, and race. So even when we're focusing particularly on one social category, like in our research, intersectionality reminds us that we cannot understand that category in isolation. Everything is in context, and there's no single universal experience of being any gender or race or religion or. Okay, so now we've been through some of the problems with the folk model. Let's talk about some of the alternative ways to theorize gender. In my work, I tend to use the lens of Judith Butler's gender performativity, which is another of those theoretical concepts that's often defined using these really intimidatingly big and philosophical words, so I'm not going to read you the quote definition. Instead, I'm just going to break it down and explain it. So to decouple sex and gender means that we are breaking the links in the heterosexual matrix. Your assigned sex does not determine your gender. There's no magical directional entailment arrow. And if gender isn't something that you are, if it's not predefined for you based on your sex assigned at birth, then it has to be something else. It becomes something you do. So by performativity, we mean all of the little things that we do intentionally or not that inform others how we do and do not fit into gendered categories. So stuff like what clothes we're wearing, how we wear our hair, whether we put makeup on or not, how we gesture, who we make friends with, and how we use language. Under this theory, gender isn't stable, by which I both mean that the way we understand gender and gendered categories differs across time, place, and social settings. So a Victorian era English noblewoman is going to have a very different understanding of gender than a farmer in the Incan Empire will. And the way that we understand and perform our own genders can also change. Anyway, this model is really nice from an NLP point of view because we can see language as being a part of performing gender. So for example, a really obvious speech act that I made when I introduced myself was to share my pronouns, and hopefully that's like helping you categorize me in a way I want to be categorized. All right, so gender is also a part of language in other ways. Syntactically, we can consider kind of three levels. There's lexical, pronominal, and or grammatical agreement. So languages like Turkish or Chinese have really minimal lexical genderings, and they don't have pronominal agreement with those lexical genderings. There's like only neutral third person pronouns for referring to people. Languages like Swedish or English have lexical gender for some cases. So we have words like man or woman, and those are gendered and sort of assigned to pronouns like he or she. But we also have a difference between animate and inanimate terms don't get this lexical gender or pronominal agreement attached to them. Other languages, like French and Arabic, have what we call grammatical gender, which is where noun classes have some degree of overlap with social gender, particularly when referring to people. So agreement in a pronominal or a grammatical sense can vary with context, like the world or the language or the social situation. For example, in our real world knowledge, we probably feel pretty comfortable filling in this choice with queen when we're trying to describe a monarch named Elizabeth, because we're probably thinking about Queen Elizabeth II of England. But if we change the context, if actually we're having a conversation about the Pirates of the Caribbean movies, then suddenly king might be the appropriate agreement. So even though these terms, king and queen, have lexical gender to some extent, and these two different entities, Elizabeths, both use the pronouns she, their agreement doesn't actually cross this like social to lexical gender gap. So we also have the level of semantics. There's the really classic Chomsky sentence that's syntactically sound but semantically incoherent. So this like colorless green ideas sleep furiously doesn't mean that much. Something can't be colorless and green at the same time. Ideas don't sleep, and sleeping furiously is a very strange concept. And then we have some sentences that are just completely unobjectionable. They're syntactically sound, and we're ready to accept the semantics. So she gave birth is an example of this. What I want to take a moment to stress here, because it's a pet peeve of mine in the literature in this field, is that swapping the pronoun to he gave birth does not make this sentence semantically incoherent. It's statistically unlikely in our cisnormative world, but what this is actually signaling is that we're missing a piece of context that explains the semantics. So who is he? Evidently not a cis man. To summarize this section about gender, and if you take nothing else away from today, I'd be very pleased if it's this. Gender isn't binary, it's not stable, and it's not physical. It's a social construct, which means that it's culturally informed and changes over time. Gender is something you do. We produce and reproduce our genders and our understanding of gendered categories via repeated actions and interactions over time. So now we're done with the first half, and let's talk about bias, the other half of this term that we're trying to define. What is bias? Unfortunately, bias is one of those terms that gets used differently in different contexts. So depending on how they specialize and what they're usually working with, people may mean prejudice when they say bias. They might also mean statistical skew. They might mean under and overfitting if they're machine learning people. There's also a difference in like the bias inherent and implicit in an individual human versus the bias in our structures and systems and societies. So the language all gets really messy really fast. For our purposes, the key is that bias causes harm. And Carolyne, I think, will go into more detail on this taxonomy, but this is from Kate Crawford, and her taxonomy splits different kinds of harms. So we have harms of allocation, which have to do with who get what resources, and harms of representation, which have to do with how people are portrayed. Language is one of the primary ways that bias is transmitted between people, which is part of why bias in NLP is such a big deal. So this can be really overt, like this sign from 1950s America, "We want white tenants in our white community." That's obviously communicating a racist message in a way that's completely unacceptable to most modern readers. But the same biases are still being transmitted in more subtle ways. And I'm sorry to have to bring up my ex-president again. But this phrase low-income housing is what's called a dog whistle. It means the same thing as we want white tenants in our white community. It means we don't want low income, i.e. people of color, in our community. So this is more subtle. It's harder for us, especially those of us who are on the like higher end of this racial privilege scale, to identify this as harmful and biased and racist. So my favorite metaphor when we're thinking about how biases are transmitted in society is that society is kind of like poisoned air. We all need to breathe. We have a need to be social, but it still hurts us. So we can be working both for ourselves and for the systems we're designing to make sure that we're filtering what we take in so that it harms us less because we're being critical about what messages we're exposing ourselves to, and that we breathe out cleaner air so that we're contributing to improving the quality of the atmosphere in general. All right, so what does cleaner air actually look like? We're going to switch metaphors. So here we have a wall and it's a barrier to access. Obviously, the situation is unfair. This person on the left can see over the wall. These two people over here really can't. They can't access whatever's behind it. There are a few different ways to conceptualize fairness using this metaphor. So we have equality, where we treat everyone the same. That's fair, but this person on the left has been given something that they don't need, and this person on the right has been given something that they can't use. So even though we're treating everyone the same, their outcomes are not the same. Equity is about treating everyone in a way that brings them to the same level. We give people resources that match their needs. So this is what I think a lot of NLP work about bias should actually be trying for. And we should acknowledge that not every problem of unfairness has a technological solution. The ideal situation is that we have a justice-based solution, that we remove the systemic problem and the wall, but that's just not going to happen through technology alone. We can't magically make it do everything in the world. So just like how technology can't solve a problem alone, it also doesn't exist in a vacuum. It's part of a complicated system of power and influence. So for example, we can think about a spell checker. This is sort of a simplified diagram of how machine learning NLP models get made and work. There are authors who are actual humans who are producing written data, which we then use to train our model or spell checker. And then as soon as we release that model, it starts to influence the authors. The minute this little red line appears under my friend's pronouns, that's telling me, hey, the spell checker didn't think this was English enough English, so you should fix it. And whether or not I take the suggestion, my behavior has been influenced. Maybe I take it and misgender my friend, which is a huge bummer and very rude of me. Maybe I don't take the suggestion, but the social message that some expressions of gender or some pronouns are more legitimate or more English than others has been reinforced regardless. Okay, so like 12 or 15 minutes into this presentation, we're actually at the title. And I'll be honest, I'm going to leave a bunch of this to Carolyne. The short version is that the definition of gender bias in NLP is always going to vary on the application and which bits of the application we're worried about. If we have translation, maybe it's about pronouns or gendered inflections. If we have speech to text, then maybe it's about whose voices are recognized with the same, like different levels of accuracy. So instead, I'm going to talk about some of the main holes in the current approaches to finding and mitigating gender bias in text NLP, and then also what we can be doing to improve the way that we do this work. So the current standard approaches in NLP tend to ignore the existence of trans, non-binary, and gender non-conforming people. And they do this by linking physical characteristics to social or grammatical gender. So an example would be saying that an acceptable analogy in a word embedding task is man is to woman as prostate cancer is to ovarian cancer. These aren't the same diseases. They're not diagnosed at the same rates, and they don't have the same outcomes or fatalities. And they're not really equivalent body parts, even if that was a thing that existed. These approaches, or different approaches anyway, often also ignore problems with trying to pair or swap words that differ only by gender. So what I mean by this is if you have a term like man or woman and bachelor or spinster, then man or woman is pretty close. Like obviously we have different connotations about them, but the definitions and the way we use them are fairly parallel. One is masculine, one is a feminine connotation. Bachelor and spinster, if you look at the literal definitions, are one is an unmarried man, one is an unmarried woman. This seems reasonable. But spinster has a much more negative connotation than bachelor. It was for a long time and still kind of is much less acceptable to be an unmarried woman than it is to be an unmarried man. And there's no such thing as a spinster's degree, but I guarantee you that your modern English data sets are full of references to bachelor's degree. So that's not parallel either. So the way that we use words means that regardless of what their literal definitions are, they're not really pairs. Just in kind of the same way that synonyms don't really exist. Okay, generally also the entire approach of intersectionality tends to get left out, although I will say this one is improving probably the fastest in the field, but it is almost always in a US context, and it mostly deals with the intersection of gender and race, which is an important thing for us to be looking at. However, it also generally treats both of those attributes as binary. So it's looking at Black women versus white women versus Black men versus white men, which is an important factor, but still leaves a lot of people out. All right, so what can we do to be better? First, we need to reject the mantra that more data is better data. It's not. Better data is better data. And so what I mean by that is what we actually want is data that is appropriate to our task and that has been curated responsibly. That's where my research hopefully comes in. Bias statements are something that are becoming more popular. They're being required by a couple of workshops on bias, which I think is great. Basically, the idea of these is to identify the goals of whatever you're doing and also identify what you mean by terms like gender bias or your theory of gender, so that people who are reading your paper know what you're talking about. Because like we just mentioned, the definition of gender bias is going to vary depending on what you're trying to fix or look at. So to tie this to feminist research principles, if you write down your bias statement before you start the research, and then you sort of check back in periodically while you're doing the research, making your methodology choices to make sure they align with your theory, and then again when you're exploring your results and doing the write-up, just to make sure everything is like in a nice, neat narrative line. This is what's called reflexivity or reflexive practice. So you're treating your own research as itself a subject of inquiry, which I think really helps just to make like tighter, more coherent research projects. The other thing that I like to borrow from feminist research principles is positionality. So that's basically just being aware of what background, and I mean that both in an academic sense and in terms of our lived experiences that we're bringing to the table and bringing to the research. What knowledge do I have because of who I am and how my life has gone and what I've read that is contributing to how I understand my research. Also, who's absent? Whose knowledge do I not have access to? And who can I invite to the table in order to expand the knowledge that I have access to? All right, and then I evidently did not put in my reference list when I shortened these slides, but if you'd like them, please feel free to email me. That's
great. Thank you very much for your presentation. Was it finished, right?
Yep, that's it.
Okay, just wanted to make sure. Okay, great. So we have 10 minutes for the questions from the audience. Do we have any questions there? So in case if you want to, you can. Okay, so Guillaume seems to have a comment, but I'm unable. Okay. So Guillaume says not a question, but a huge thanks to Hannah for exposing all these burning problems in front of a 30 people crowd. As a society, we're really slow moving on these problematics, but hopefully we'll make it one step at a time. Congratulations. Yeah, in fact, a great topic to discuss about, and it's a big problem that exists in natural language processing, same as anything else that exists out there, and it was very important that it's covered. So I just wanted to mention that you can use the raise hand button in order to like virtually raise your hand, and I'll pass you the podium to ask your questions. And now Timia, if I'm pronouncing the name correctly, has a question.
Yes, hi. I'm just wondering, what do you suggest in terms of, because all of this is understandable, right? It comes from history, it comes from all the languages, how they are encoded. So it's not like we're gonna change it. Everybody change all their languages to genderless pronouns and all of that. So I'm just wondering, how do you suggest that we tackle this, because it's inherent the moment I need to use English and the moment I need to translate a text that I don't know if it's a he or she, I have to choose something, right? So it's like, what is your suggestion in terms of society to tackle these problems? Because as you said, if there's no context, then you just gotta choose, right? Because there is no new pronoun in English for the genderless he or she. So,
well, good news. We have a really old pronoun in English. It's they.
So you would introduce in every language, and you would delete all the le, la, il from French and everything.
Well, I don't know, because French has its own method. Like, there are people in using French in ways that are sort of playing with or rejecting the le, la binary, partially by trying to remove the association with the ideas of social gender. There are neopronouns in French, so there's il, which I'm not very good at using yet, but I'm trying to improve. And there's neomorphemes, so like ways to change the endings of words in order to be something new that's not really either masculine or feminine. So language, I think, is evolving, and it always is. And I think the thing you said about choice is really important, right? So if we have this machine translation system, depending on what the system is trying to do, it might not actually be important that we make a choice. We could give options. And this is something that Google Translate has been like trying to do, because they keep getting in trouble for being biased and stereotypical in their translations. So in some cases, not all, because they haven't fixed all of the cases. But in some cases, if you say like, my friend is a doctor, and try to translate that from English into French or Spanish, you'll get both the masculine and feminine doctors out, and Google lets you pick. So just having notes about what you could be doing, or where a neutral option is available, like using that as default and letting a user pick which one they would prefer.
And can I have another question? You said that synonyms don't really exist. Can you elaborate on that?
Yeah, I can. They don't. There are words that are really related to each other, but they're not exactly the same word, because if they were, we wouldn't have two of them. So a great example of this in English is we have the noun phrase butt dial, which means to call someone accidentally. And another word for butt is booty, and another word to dial, as in the verb, is to call. But a booty call is an entirely different concept. So we have these words that are like nominally related and mean the same thing in some contexts, but if you put them together in other contexts, they do not mean the same thing anymore.
But I guess that's not the definition of a synonym. So synonym is like pretty and beautiful, right? So that they kind of
but pretty
mean
and beautiful
semantically the same thing.
But do pretty and beautiful actually mean the same thing? For me, pretty is a little more diminutive, and beautiful implies like a level of elegance that pretty doesn't. They have different connotations. Yeah,
so synonym doesn't mean they're equal words. It just means they're very, very close in a sense, in their sense.
Yes, I think this is the kind of thing that like linguists argue about and get into fights a lot. So it depends on what definition you want to use. In the sense of words that are an exact match for each other, there's not really such a thing. In the sense of words that have very similar senses and are often interchangeable, yeah, obviously we have those.
Mm-hmm. Okay, thank you.
Thank you very much. So do we have more questions from the audience? So I might have a question on that topic. So considering that language models generally try to model three different aspects of the language, which is the syntax, semantic, and to some extent the common sense, is it correct to assume that the most harmful type of bias in the language model is the one that comes from the common sense aspect of it?
How do you mean?
Like the example that you showed. So in the common sense, like for example, the case that you mentioned, that if there is like a nurse, the pronoun that is assigned to it is usually a she, because in general, statistically, it's more probable. Or like by common sense is what I mean is that usually when they're trying to solve the problem of the common sense is what is more statistically possible, like at least based on the observations that we have so far in the data. So is that correct to assume that this is the most problematic one?
I think so, but I think that's specifically because when we say common sense, what we sort of mean is social knowledge, and the society we're in and the knowledge we get from it has all of these stereotypes and prejudices and negative associations built into it. So like that is being picked up on other levels and other senses. But yeah, I would say that that's really the thing we're objecting to mostly.
Yeah. So basically, one of the biggest challenge, would it be correct to assume that the biggest challenge is to trying to separate stereotypes from the common sense?
Yeah, or like, I don't know, I think there's a level of universal design you can do to sort of remove common sense knowledge. Image captioning systems. There's been some research into basically the problem of looking at the context to gender. So someone standing in a kitchen is much more likely to be labeled, sorry, my cat is knocking things over, is much more likely to be labeled a woman than a man. But there's actually like no real reason, unless we know what specific person it is, to make that label at all. Like we're only we could just say a person in a kitchen. Or someone is standing in a kitchen.
Thank you. Do we have more questions from the audience? So once again, I need to mention that in the panel, like right beside the screen, maybe above, maybe below. There is like where you can see the option to mute or use the camera. There is a hand icon, which if you use, you'll virtually raise your hand, and I'll be able to pass the podium to you. Okay. So it seems like there are no more questions. So once again, thank you very much for your very exciting presentations, Hannah, and thanks everyone for the questions. We're moving on to the next talk, which is, as far as I've realized, is going to be a follow-up on this one by Carolyne Pelletier, who is a co-founder and CTO at skritswap, sorry.
It's hard to say.
And the presentation title is Gender Bias in Natural Language Processing. Sorry for my problem in pronouncing the name. So without further ado, the floor is yours, Carolyne.
Thank you so much. I was just saying it's actually quite difficult to say. We might change the name. So I'm going to go ahead and share my screen here before we get started. Okay.
Perfect.
Okay, wonderful. Everyone should be able to see my screen?
Yes.
Okay, great. Just trying to see. Okay, cameras, wonderful. Okay, so let's get started. Hello, everyone. My name is Carolyne Pelletier. I'm currently the co-founder and CTO at skritswap. So this is an AI startup that simplifies the jargon in your contracts by providing simpler language and clearer formatting. We do this using NLP. So previous to this, I was a grad student at Mila, and where I did a lot of my work in gender bias in natural language processing. And I also co-founded a group called Biasly AI. So this is a group of researchers in Professor Yoshua Bengio's humanitarian AI group at Mila that are committed to combating biases in AI, such as gender bias, racial bias, sexual orientation bias. And if you're interested in this group, there's a website on the Mila main website where they hire interns, and they're a fully funded group of really exciting researchers. So I'd encourage you to check them out. Okay. So today, here is the main objective of my talk. Thankfully, Hannah and I spoke yesterday because our talks, there was a bit of an overlap in the topic, but because Hannah went over the definition of bias, I will thankfully not go through that because her definitions are a lot better than mine, to be honest. They're a lot more well-defined. And so I'm going to go right into gender bias in AI systems. How do NLP systems acquire knowledge? Where does data bias come from? And then I'll go into my own research, which is bias in language understanding models, which is divided into 3 parts. So there's an understanding component, a measuring component, and a mitigation attempt. And we'll talk about this disclaimer here. It's an attempt. It's not a okay. So I did this. There's no more bias. Let's move on. So we'll discuss that, and then some questions at the end. So let's just, generally talk about gender bias in AI systems. We've seen some examples happening in production with companies like Google. This Amazon example, I don't believe is an example in production. This was an internal tool that was thankfully not released. And we all know that in AI, is only as good as your data. So when you have supervised learning, all of the biases that are in your data set are often amplified. And there's a big importance on having clean data sets but not only having clean data sets, but also knowing what is in your data set. So doing demographics on your data set, seeing if there's sensitive attributes. Are you modeling gender? Are you modeling race? Even if you're not modeling gender or race directly, are there other features in your data set, perhaps like a postal code, for example, could give a lot of indications on race. So, you know, you always have to keep in mind that even if a particular sensitive attribute is not present in your data set explicitly, there could be implicit correlations between this, and it's very important to you know, have that in mind when you're making decisions, predictive decisions based off of your data. So the work today is, you know, in gender bias, and I kind of put this slide here because gender bias is a bit of an overused term. Bias in general is quite overused, and Hannah did a wonderful job at defining the different types of biases. So we have bias in writing, and which is typically largely qualitatively defined. Usually it's presented in guidebooks and guidelines. And when we look at gender bias in machine learning, this is largely quantitatively defined. So, you know, things in word embeddings, coreference resolution, language models, machine translation. And I encourage you to check out this wonderful literature review by Sun et al. That gives you kind of this overview of all the different types of gender biases. Great. So I'm going to go into a few examples of gender bias in natural language processing. The first one that you see here is gender bias in machine translation. Hannah might have shown this, but so we have here Hungarian on the left. Hungarian is a genderless language. So this made its rounds on Twitter, I think quite recently. And when you translate this paragraph, you see that the English model, or the translation from English to Hungarian to English, has to make decisions on a pronoun. And it does so in a stereotypical way, which you see here on the right. And, you know, it's quite a complicated problem. It's not, you know, just an issue with the data or just an issue with the algorithm. It could also be an issue with how the model, you know, chooses to chooses the top prediction. So there could be problems with maximum likelihood. Perhaps the top prediction is inaccurate. The output does not reflect the model. And there could be a problem with reality. So it's not how it is. Biases reinforce, and then the biases are reinforced by these machine learning models. And you know, this is a nice little YouTube video that Yannick Kilcher did to talk about that specific machine translation model. But all that to say is that it's a complicated problem, and you can't just reduce it, for example, to it's just the data. It's an overarching problem. And I'd also like to mention that, you know, there's work by Melvin Johnson, who's the senior software engineer at Google Research, that they are working on gender-specific translations. So you see here on the left, my friend is a doctor. There's the Spanish version here. And then in gender-specific translations, you would have both options. So this is in production right now. You can try it out. The trick, though, is that when you input a whole paragraph like here, it doesn't do the gender-specific translations, but if you tokenize it at the sentence level, you would actually see gender-specific translations. So a big part of these models is also knowing how to use them. And I think one of the issues is that, you know, we're super users of these models. We know that there are biases, and we are aware. But I think the problem arises is when the general population that don't necessarily have a technical background go on Google Translate and use these models without realizing that there could be, you know, potential issues. Another example of gender bias in NLP would be co-reference resolution. So co-reference resolution is the task of finding all expressions that refer to the same entity in a text. So this is work by Zhao et al. And they consider the system to be gender biased if it links pronouns to occupations dominated by the gender of the pronoun. So they call this pro-stereotypical situation. So this would be, for example, the physician hired the secretary because he was overwhelmed with clients. So in that case, physician, the stereotypical situation would be with he, and the anti-stereotypical situation would be linked with she. So this work was really, they created a evaluation corpus to see if gender bias in co-reference resolution exists. So that was the whole goal of this work. And it, the counterexample it doesn't hold. So you can't say that a system is free of gender bias if it passes the test. That's not what this evaluation data says. It really just, certifies if gender bias in co-reference resolution is present. So, when you're thinking about where does this data bias come from, if you'd like more information on this, there's a wonderful course by Ivado, Gornouche Farnadi, which is an assistant professor at HEC, and is a core faculty member at Mila, does a wonderful course. It's free and it's delivered through the EDX platform. They go into more details about where does this data bias come from. So there's population biases, behavioral biases, content production biases, linking biases, temporal biases. This is very interesting work on looking at where it comes from through the lens of a social media example. So I found this very compelling. And they go through, the machine learning pipeline. So it happens in the pre-processing phase, in the in-processing phase, and in the post-processing phase. So it really outlines how complicated and difficult these issues of biases are. Great, so now I'm going to get into some work done at Biasly AI under the humanitarian AI for Humanities, group at Mila. So the goal of this work was to correct for gender bias in text, much like a spell checker would. And, so you can imagine a scenario like this, where this is a Microsoft gender neutral language checker. So you see here the sentence, the salesman went on a business trip, and then it says, consider using gender neutral language. So there's an alternative salesperson. And this was the general idea of this project, was to say, okay, so this is one type of gender bias. Are there other types of gender bias that we could perhaps correct in text? And we first started by consulting experts. So, it's very important, especially when you have just a background. So our background was mainly in computer science, machine learning. It's extremely important to reach out to the social science and reach out to experts in gender studies, much like Hannah, who have a much better understanding of, definitions of gender bias. We did learn a lot about, different expressions of gender, so male, female, non-binary, neo-pronouns, which we weren't aware of before. And if you don't reach out, you don't do that research, then your machine learning research will not be inclusive, and it's, damaging to downstream applications. So we spent the time consulting with experts, and the main feedback from experts is that it's not always easy to come up with a one-size-fits-all definition for gender bias, because again, the goal is to fix gender bias in text, and so we were wondering, what is the definition of gender bias in text? So we saw the Microsoft Word example, that's one definition, but are there other types? And the definitions differ across different languages and cultures. So, this is specific to English, this is specific to Western culture, and there are subtypes of gender bias. So this was our attempt to quantify gender bias. And our definition is, we divided it in structural and contextual type of gender bias. So gender bias found in the construction of the sentence would be gender pronoun bias and explicit marking of sex, and then bias found in the context. So that would be societal stereotypes and behavioral stereotypes. And here are more examples of what I mean by that. So gender pronoun bias, it's when we have a gender neutral term referred to by a gendered pronoun. So a programmer must always carry his laptop. We would call that gender bias. And there's an assumption here that a programmer is his, and it should be their laptop. And then explicit marking of sex. This is similar to the Microsoft Word example, where if you can, replace a keyword with a gender neutral version, then that should be done. And then we get into the contextual type of gender bias. So we have societal stereotypes. Senators need their wives to support them throughout their campaign, and assumes that all senators have wives, or just assumes that it just makes a lot of assumptions that does not make it inclusive. And then we have behavioral stereotypes, where all boys are aggressive is kind of based on behavior. And again, so the goal was to, capture gender bias in text. And the first thing we did was create the taxonomy. And then the next step was to collect data points so that on one type of gender bias, so that we can train a machine learning model to identify and correct for that type of gender bias. So the first step is the identification. So we're like, okay, let's find a ton of data sets. Let's look at a ton of data sets, and let's filter out the sentences that we know are not biased, so that we can have a pool of candidates that are perhaps biased. And we got that pool of candidates labeled by annotators. So we had to choose one type of gender bias. I'll go back here. We chose the gender pronoun bias to capture in text. And again, we did this by taking existing data sets and by filtering out using a hierarchical filtering model. By filtering out sentences we knew that were not gender pronoun bias, so that we were left with a pool of candidates, and we got this pool of candidates labeled. And there are definitely flaws to pre-trained models when you're doing this, when you have this hierarchical example. So if your co-reference resolution model doesn't work, then you'll have a cascading error where your other pre-trained models won't work either. So there are pros and cons, but the main results were that 3% of all these data sets passed our filters, meaning like that was the pool of candidates that perhaps had gender pronoun bias, and about half of that 3% were labeled as gender pronoun bias. So that gives you a bit of an idea of like the percentage of gender pronoun bias in the particular data sets that we chose. Okay, so now I'm going to move on to how do NLP systems acquire knowledge about the world? Is it by reading large amounts of text? And one of the biggest challenges in NLP is that there's a shortage of training data. And when I say shortage of training data, I mean before the days of fine-tuning on Wikipedia and Book Corpus and the whole kind of web, training sets were very small, very specific. And I guess that would be our fine-tuning data sets today. And what's been successful in these recent years to combat this is to leverage unlabeled data sets to better train supervised models. So this works by either training word embeddings and then using those word embeddings as input features to your supervised model, or you treat it as a problem, or you treat the problem as a transfer learning problem and you fine tune on a supervised task. So what's been, that latter example of what I talked about. So these are all the successful models like BERT that pre-train on large amounts of unlabeled data using a particular objective, and then you fine tune it on a specific supervised task like sentiment analysis. This is what's been working really well recently in NLP. And I always think about what is actually captured in text. So when we tell these models, okay, read the whole web, what are they actually reading? And what the problem is that the text on the web doesn't capture the beautiful diversity in humans. So things that are not well represented in text are all the different languages. So yes, we have a ton of English text, but what about all the different smaller languages that perhaps are not even on the web? That's an issue. And other things that are not well represented are sensitive attributes such as gender, ethnicity, sexuality, disability. They are not always all represented in equal manner. And this causes a lot of problems. And so, I will listen to some of the questions, and there was a question about common sense knowledge. And so these are the types of information that are key for NLP systems to understand when they're interacting with people. And they're quite often difficult to capture in text, like all these nuances, but humans can do this a lot better than NLP models. So as an example here, so the frequency in text doesn't always match the frequency in the real world. So for example, the person breathes the air. So we have two sentences. The person breathes the air and the dentist breathes the helium. Both sentences, as a human, we would say they're both probable. They both exist. They're both non-zero. But a language model won't think that the second sentence is probable at all. It would probably, give it a very low probability, which, it's an issue because it kind of reflects that events that are not commonly described in text won't ever be probable in these models. And it's not, I guess, an exact reflection of the real world. Other things like stereotyping, though, here is a Ngram viewer by Google. So here we see that the frequency in text kind of matches the frequency in the real world. And there's work that kind of backs this up a bit better than what I'm saying right now. But the top red line here is she works as a nurse, and the bottom is he works as a nurse. So stereotyping is a kind of a different scenario. So for the last few minutes here, I believe I have about 5-6 minutes. I'm going to quickly go over my work on pronoun bias and language understanding models. I'm happy to share my slides after because, again, I have quite not that much time to go over quite extensive work, but I'll do a summary. So this work is divided into understanding pronoun bias, measuring pronoun bias, and mitigating pronoun bias in language understanding models, more specifically BERT. And Hannah had mentioned the bias statement. I didn't have it in my slides before, but I quickly copy-pasted my bias statement because it is very important to have a bias statement when you are working in gender bias. So I'm not going to read all of this. It's quite long, but you can see here that we are concerned about allocation harms. And, continued, and it's very important to define exactly what pronoun bias or what type of bias you're referring to. The more information you can provide, the better for the reader. So, we say the term pronoun bias refers to the prediction imbalance related to pronouns in the mass language modeling task. And, to talk a small, very quick resume on BERT, BERT pre-trains on Wikipedia and book corpus, and its pre-training tasks are mass language modeling and next sentence prediction. And you see here the problem that we're looking to attack here is that in mass language modeling, so you mask out, the doctor ran to the emergency room to see masked patient. It predicts his at a probability of 38% versus her at a probability of 6. So there's quite a big disparity here. And here, here's some nice slide from Hannah, which shows the different ways in which you can measure gender bias. We choose to measure the performance differences. And here are different ways, again, slides from Hannah, to mitigate gender bias. And we choose to do both the manipulating data and manipulating the model. So the first part is understanding where this gender bias comes from. And we do this by looking at the training data of BERT, that's book corpus and English Wikipedia. We have a counting algorithm that counts co-reference resolution clusters and co-occurrence counts. So, it goes through all of the training data of Wikipedia and book corpus, and it will, count, it will look at a finite list of occupations. So here's the finite list of occupations based on this US Department of Labor statistics. And here you can see that the occupations are on the x-axis, and here you see here the pronouns are in different colors. And when you look at a quick glance, you can see this is Wikipedia and book corpus, and you can see at quick glance that the he, him, his pronouns dominate the co-occurrence counts in Wikipedia and book corpus. And it is the same, also it's the same thing for co-reference resolution. So co-reference resolution is, again, tying entities together. So you see here, it's kind of the same trend with co-reference resolution. So that was kind of the first part of understanding, where does this bias come from? You can see here that it gives us a bit of an indication. Next part is measuring gender, measuring this bias in BERT. So we use the association score here. It's called a template technique. And we have a set of templates where we, initialize these occupations with all the occupations you saw before. And then these subjective, objective, and possessive are pronouns. And we try to make a diverse data set, diverse templates as possible with different, subjective, possessive, objective. And this evaluation data set ends up being around 1,920 data points. And so we use this measuring technique by Carita et al. To get an association score for BERT, kind of a baseline. And we can see that there's a correlation between the training data counts and the association score. So what this means is that, as the co-occurrence count increases, so does the association score. And this is kind of a nice finding, because if you can't run the counting algorithm on your training data because it's quite computationally expensive to do this, then this association score, which is run at inference time, could perhaps be used instead. The last part is the mitigation attempt. So again, disclaimer, this won't work in every case. There's no guarantees that a system will be free of bias using these techniques. So our mitigation attempt is of the thought that we can choose curated data sets that have statistical properties that are beneficial in kind of helping us out with this association score and this pronoun bias. So we used two examples here, GAP and MAP. And we also used a technique called name-based counterfactual data substitution on top of GAP and MAP, so on GAP and MAP. And so name-based counterfactual substitution, so it's an improvement on counterfactual data augmentation. It avoids text duplication, and it also has a names intervention. And I'll quickly show you an example to show you what I'm talking about. So you see here, gap, we have Zoe Telford played the police officer girlfriend of Simon Maggie. Gap with CDS would say Carl Telford played the police officer boyfriend of Estelle Darren. So the idea of this intervention is it tries to maintain the context of the sentence, but it changes the names, and it changes also a finite list of gender terms. And the idea is that we're trying to get different genders in different contexts to combat these types of biases. And so wrapping up with some preliminary results here. Ideally, you would want, this is our baseline, BERT, and what we're looking at is the prediction count normalized. So these are counts for each target demographic. Ideally, you would want these counts to be quite equal. Like you would want them to be like all equal across the board. This is our baseline with BERT. This is what it looks like when you fine tune on the GAP data set. So you see that there's some improvements. Again, when you fine tune on GAP with CDS, it's not as, I guess, spiky as the BERT base. Here we go when you fine tune on the MAP data set, MAP with CDS. The fun thing about the MAP data set is that it's a data set that includes gender neutral pronouns. So you can see here that with BERT, again, the ideal scenario would be that all of these numbers would be quite equal. But you can see here with the MAP data set that includes gender neutral pronouns that at least they're non-zero in the prediction counts. So when I say prediction counts, again, I'm asking the model to predict what the pronoun is, and we're getting non-zero situations with MAP. And if you're interested in more information in this work, you know, you can, we will be releasing all of our results quite soon. So, you know, all of the graphs that I just showed are, you know, backed up by actual association scores. So here, green means that the association score moved in a good direction, so that'd be towards 0. And red means that the association score moved in a bad direction, that's away from 0. And we always compare it to our baseline BERT. And you know, part of this work, so we have an understanding, measuring, and mitigation attempt. All of this is really to bring everything into a specific use case in gender bias and machine translation. We're going to use the information that we learned in that work to, you know, make it in a robust use case that could be useful for models that are used in production. That's it, and thank you very much, and I'll take some questions.
Thank you very much for your very exciting presentation. So we have about 10 minutes for the questions from the audience. So do we have any questions there? So for now, I'm going to ask a question, like a basic one. I may have missed that part, but the data sets that you created in order for the GAP and the CAS, don't remember the name. So the creation of those data sets, was it manual or was it an automatic process?
Yeah, thank you. These data sets are not our own data sets. These are from existing researchers. So GAP is called the Gender Ambiguous Pronoun Data Set. It's a gender balanced data set that contains co-reference labeled pairs. So the idea with GAP is that it's gender balanced. And so when you fine tune on a data set that's gender balanced, our hope is that it will move the association score in a manner that is you know, beneficial. Because GAP only represented binary pronouns, we were interested in finding a data set that also include gender neutral pronouns. And so that's why we also included the MAP data set. So MAP data set, again, so both of them are from Wikipedia. they choose sentences within Wikipedia that fits their data set. And these curated data sets are they're very valuable in if you have a specific task to accomplish, then our specific task was to move the association score in a way that's beneficial for pronoun bias. And these two data sets are at least a good kind of first step in seeing if the association score will budge or not. It's not a perfect solution. Again, I think the perfect solution would be starting from scratch and like really saying, okay, this is our problem, and let's curate it from scratch. But that's computationally expensive, and this is research. So we started off with GAP and MAP, released by other researchers, where I must say their intention of these data sets were not necessarily for our use case. And that's not, you have to, for sure, you have to keep that in mind. And in my work, I define it. I say GAP is for co-reference resolution. MAP is for co-reference resolution and annotations. That's the specific use case that they use it for. We are going to use it for something different. This is what we're using it for. But you have to definitely include those disclaimers.
Okay, great, thanks. A follow-up question on that. So you mentioned that you use a pre-trained BERT model and you fine-tuned it on these particular data sets in order to mitigate the problem of the gender bias.
Exactly.
So I was wondering, how would you see the final effect if you could actually incorporate these data sets or the samples from this data set during the pre-training phase of the BERT model itself in order to see how it would change. And also another question was that when you were fine-tuning on these, did you also try fine-tuning on a regular NLP task, like a common one, in order to see if the performance has actually changed from the original performance? Could we still reach the same performance or a competitive performance as it was from the original BERT or not?
So yes, so you're talking about a different pre-training task. So is your question, hold on, I'm gonna go back here. Here we go. So BERT's pre-training tasks are MLM and next sentence prediction. When we fine-tune using MLM. So we're in our minds, it's kind of extending the pre-training task. So is your question, did we try a different objective to fine tune?
No, I was saying that instead of doing the mass length, on the original data set, and then to continue pre-training on the bias handling data set, why not to fit the data sets that try to mitigate the bias problem within the original training one?
Okay.
Try to fit in the original data.
Yeah, absolutely. So I think the first, so book corpus and English Wikipedia are massive, massive data sets. And so if we were to so these fine-tuning data sets are comparatively extremely small. They're, I wanted to add a slide that shows, I should show a slide that shows how much smaller these fine-tuning data sets are to the pre-training data sets. And so I believe if we just included the fine-tuning data sets in the pre-training, they would just get lost in their statistical effects would be lost within book corpus and Wikipedia. Do you understand? If I just threw in 5,000 data points into these massive data sets, they would no longer have an effect on BERT, pretty much. So,
No, I understand, but I'm sorry to interrupt you, but why not try to upsample these small data sets? Try to repeat them as frequently so that their effect becomes bolder.
Absolutely. So we do look at different types of augmentation, and we found that, I'm just trying to find CDS here. Here we go. So see here how we go. So we do it with GAP alone, and then we do it with GAP CDS. We also tried different types. So CDS is a in-place substitution method. So it doesn't actually increase the count on your data set. So if you have 5K gap, then you'll have 5K CDS. But we also tried it with counterfactual data augmentation, which actually increases the data set from 5 to 10, for example. And we found that duplication for some reason didn't help, because in augmentation you'll have a sentence like, she goes to the store, the doctor runs to the store, or whatever. The doctor takes care of her clients, and then they'll be duplicated in this data set. The doctor takes care of his clients, and they kind of like cancel each other out. And so, I mean, there's a better explanation for this in this paper here, actually this one here, Maudsley et al. They kind of make a case as to why in-place substitution is better than data augmentation for the reason of text duplication fares worse in compared to substitution. So I think Hannah mentioned this in her talk, more data is not always better in these types of scenarios of when you have these fine-tuned data sets that have a specific purpose. You know, more data is often better in the pre-training phase, where like you want to capture as much information as possible. But in the fine-tuning phase, more data is not always better. It's obviously beneficial, but you need to do it in a very, careful way. If that answered your question correctly.
Yeah, perfectly. Thank you very much. So do we have questions from the audience? Yes, Malik has a question. Please go ahead.
Hi, thank you for the very impressive work. So I agree with the point that data is not always helpful, but maybe if we're talking about specific languages or certain tasks, then we can see that there are some languages that exhibit less bias or tendency for bias, like the examples that you have shown with, was Hungarian, I think, English, I think?
Yeah. Okay,
so maybe, do you think we should use these languages more in our tasks, like specifically in translation? And instead of having, I know most models use English as a pivot language when translating from one language to the other, especially with these ones with low resources. So should we put more focus on these languages instead of English, or maybe translate our task to this language and solve the task and translate it back? What do you think about this?
Absolutely, and that's exactly where all of this work is going into. You kind of like, you hit the nail there. So, we're looking at what happens when we're looking at this, pretty much like what happens with these genderless languages in machine translations. There are ways to go from genderless to English, English back to genderless, or French to English. And so our next work is exactly this. So kind of taking what we learned with understanding, measuring, and mitigating, and seeing how we can associate this with these machine translation models, and then seeing if we can leverage some of the genderless properties to the gendered languages, and see if we can inform those models to make more inclusive predictions or not so stereotypical predictions. So yeah, it's definitely it's our next direction, and we're hoping to have it released by the end of the summer or September.
Thank you very much. Thank you, and good luck. Good luck with that.
Thank you.
Thank you very much again for your very exciting presentation, Caroline, and thanks, Malik, for the question. And once again, I'd like to overview today's presentation. We had 3 exciting talks by Eloi, Hannah, and Carolyne, and all of them, it was really exciting and we really enjoyed them. Thank you very much for your exciting presentations, and thanks everyone for attending today's event. So that pretty much concludes this season from the Montreal NLP Consortium Meetups. Our upcoming event is going to be on September 23rd. And please stay tuned for more news about the upcoming event. And lastly, the recording will be provided by Guillaume at the within a few hours. And also during the during that email, there's also a survey that will be provided for you. So it would be great if you can kindly take the time to fill out the survey and provide us with your invaluable feedback so that we can use it and leverage it to better improve our upcoming meetup events. So we are all looking forward to meeting every one of you back in September 23rd. And until then, stay safe and enjoy your days. Bye.